Okay, so for the time being at least, let's stick with the book. So today we will be discussing what's called the adiabatic approximation. A new kind of approximation. Well, the kind of problem that we will study, for example, it also has the classical analog. So just look at this one, it's making oscillation. Well, if I just move this hanging point from point to point, it will still keep doing the same oscillation. Nothing will change. Of course, if I shake it violently, the oscillation will change. But as long as I keep the motion small, nothing will change. That is the basics of the adiabatic approximation. So, just as in this problem, we will assume that we have the Hamiltonian, which, well, as usual, it depends on the momentum and the coordinates, the corresponding operators. But it will also depend on some parameters. Let's call them lambda. And these parameters can change in time. So this is the kind of problem we will be analyzing. Like in this problem, this hanging point is changing in time. So lambda is the suspension point in this problem. And we will see how the state... Now what we will be showing is that, let's say that we have hi is equal to h evaluate that t is equal to initial time, and hf is equal to h when t is equal to t final. Each one has its set of eigenstates. Psi hi, psi I n is equal to e n I psi n I, and hf is psi nf. Hn acting on psi nf is e nf psi nf. So the initial Hamiltonian and the final Hamiltonian, they all have their eigenvalues, their eigenstates, etc. This is the time-independent eigenvalues. Now, if there is a state psi that at t is equal to 0, x, this is equal to psi n of I t, now psi n of I, not t, x, we will prove that psi at t is equal to large T, x, is equal to psi and f of x, up to some phase. So if you start with the nth state, nth excitation, then after this changing of the parameters, your system is now different, but nevertheless your state is still in the nth state. So if you start with the ground state of hi, at the end of your time, you will be in the ground state of hf, whatever that ground state is. And up to now, we have been mainly dealing with perturbations, which assume that changes were small. In this case, you can have a large change. The change can be large, but nevertheless, the rate of change should be small. Now, first, let's see whether this actually works or not. Now, this is what we are aiming to prove. But if this is not correct, there's no point in trying to prove it. So let's look at an example where we can actually solve it. Now we will look at the particle in a box. Which has this potential V is equal to 0 if x is less than 0 or x is larger than, let's say, omega of t, and infinite otherwise. So basically we have this box. This is V of r as a function of V of x as a function of x. So there is this infinite wall, and this wall is moving in this direction. So omega of t is, let's say, a plus v of t, and that is moving with velocity v. No, x is infinite if, okay. Now we already know at a given particular time, we know the energy eigenvalues already. So h of t, psi of t, x of t, psi n of x of t, this is equal to E n of t, psi n of x of t. The solution of this one is psi n of x of t is equal to sine n pi x over omega of t. So it's not time independent wave function. The wave function depends on the time because it depends on the parameter which depends on the time. So what's the normalization? What's the normalization? Time dependent, but the value? So this is our wave function. Now, of course, this is not the solution of the time-dependent Schrödinger equation. We would rather find the solution of the time-dependent Schrödinger equation. So h of t, let me use the phi n of x of t. This should be equal to I h bar derivative of phi n by del t. So it would be nice if at every time it is our psi n or a linear combination. Now psi n's are just a complete set. Although they are time dependent, they are complete. So any function we can expand in terms of those. Now let's try to find the solution of this form is equal to psi n of x of t. Well, of course, this is the solution of the time-independent Schrödinger equation, not the time-dependent one. So let's add some time dependence. And maybe even some x dependence, we don't know. Hopefully we will get rid of that x dependence of the f. And see what is the equation satisfied by f. Now, the boundary condition we will impose on f is that if omega is time independent, f should be 1. Now, d phi by dt is just d psi by dt, f plus psi df by dt. And d squared phi by dt squared would be d squared psi by dt squared, f plus twice psi prime f prime plus f double prime. And that psi by del t, and that phi by del t will be equal to del psi by del t, f plus del f by del t times psi. And we will just put this in the Schrödinger equation, h squared over 2m del squared phi by del t squared plus v of x and t phi. This is equal to I h bar del phi by del t. F double prime psi. By the way, energy changes with time. So energy is not conserved. How come? True. I mean, something is moving the wall, so it has to exert some force on our system. So there's some work, something doing some work on our system, so energy need not be conserved anyway. So let's continue. This is the Schrödinger equation that we are trying to solve. Minus h bar squared over 2m. No, del x, sorry. Psi double prime f plus twice psi prime f prime plus psi f double prime plus v psi f. This should be equal to I h bar. Sorry, I would like to add one more thing to this derivation. Of course, we need to change it a bit. We already know what the, if our state, if our parameter is not changing in time, we already know what the time dependence of the energy is. It should be e to the power minus I over h bar, En times t. Now, in this case, En will be changing in time. So let's just, instead of multiplying it by t, let's just integrate it. So this is the solution. I mean, if you forget about the f, this is the solution. That is the solution that satisfies the time-dependent Schrödinger equation. Time-independent Schrödinger equation, sorry, without f, because the derivative of that exponent over there is nothing but En, if you ignore the time dependence of psi. So if the parameter was not changing, then psi n would be independent of t. It will be there, and that exponent will be there. And since now the parameters are changing, we would like to see how this state, our solution is modified, so we add this function f, this unknown function f. And that is what we are trying to find. And if the parameters were constant, that is the derivative of w with respect to time is constant, then f should be 1, constant. Or just an arbitrary phase at most. So what changes here, okay, so here these should be the x derivatives. They all contain this exponent. And here we have one more term, minus I over h bar e of t psi f. E to the power minus I over h bar e of t prime dt prime from 0 to t prime. Now it is clear why I am looking for such a form. I could have absorbed that exponent into the definition of f. But since I'm looking for deviations from my solution when the parameter is changing, I would rather separate it. That factor would have been there whether my parameter is changing in time or not. If my parameter is not changing in time, that En of t prime would have been just a constant. And so the integral just gives me e times t. And since my parameter is changing, I have the psi n depends on time through my parameter. Plus there's some additional possible time-dependent pieces, which is f. Now everything has the same exponent, so when you write in the Schrödinger equation, the exponent will be there on the left-hand side and also on the right-hand side, so I just cancel them. And so this is what remains. I h bar psi dot f plus f dot psi minus I over h bar e of t psi times f. But you see, psi already satisfies this equation, minus h bar squared over 2m psi double prime plus v psi is equal to e of t psi. Psi already satisfies this equation. That is how we chose psi to start with. And v can depend on x and also on t. So this term and this term, they all cancel. Yes, they are all proportional to f. So when I multiply I h bar with minus I over h bars cancel, I times minus I is 1. On the left-hand side, I have minus h bar squared over 2m psi double prime plus v times psi, both of them multiplied with f. But that is just e times psi multiplied with f, which I also have on the right-hand side. Now, psi is the solution of this one. Phi is the solution of the time-dependent Hamiltonian. Time-dependent Schrödinger equation, sorry, not the time-dependent Hamiltonian. Psi is the solution of the eigenvalue equation for the time-dependent Hamiltonian. That is psi. Phi is the solution of the time-dependent Schrödinger equation. You see, at any time, we have a Hamiltonian, and we can write the eigenvalue equation for that Hamiltonian. And the solutions, I just call them psi. But what we are actually interested in is the solution of the time-dependent Schrödinger equation. Now, if my Hamiltonian is time-independent, then the solution of the time-independent Hamiltonian gives me the eigenvalues, and I already know their time dependence. But now the Hamiltonian has some parameters which are changing in time, so the solution of the time-independent Hamiltonian might be a bit more complex, in the sense that phi n of xt, okay, if the parameters were not changing, psi n would be independent of time. I would have that En would be independent of time. That would be the energy dependence, and f would have been just 1. Now I'm looking for a solution of the time-dependent Schrödinger equation, which is equal to psi n of xt at t equal to 0. That is my initial condition. And so the question is, how does it change with time? And I just postulate that phi n is my solution if parameters were not changing in time, with the only modification that energy can be time dependent, so I'm taking the integral of the energy in the exponent, multiply it with some factor that is due to the time dependence of my parameters, and see if I can find that f. If I can find that f, then the uniqueness of the solution tells me that that's the only solution. And then I'm looking for an equation satisfied by f. That is what I was looking for. Now I have this equation. So I have that cancellation, minus h bar squared over 2m 2 psi prime f prime plus psi f double prime should be equal to I h bar psi dot f plus f dot psi. Now this is 2. Now this is what I need to solve. So what is your proposal? Okay, that is one choice. We are looking for one solution that satisfies our initial conditions. If we can find one, no matter how we find one, the uniqueness already tells me that the solution is unique. Do you agree?
I don't understand.
So you see, we have our differential. Let's look at it from a mathematical perspective. Let's forget about the physics for a time being. What we are saying is we are looking for a solution of the time-dependent Schrödinger equation. This one. And the thing is, if we can find one solution by whichever trick we use, satisfying our differential equation plus the initial condition, then the solution is unique. So that should be the only solution. So since the solution is unique, if we find one by whatever approximation we do, not approximation, whatever assumption we do, if we can find one, that is the only one. So what we did here is, this form, well, any function I can write in this form. So I'm kind of factoring out one known time dependence, one known time and position dependence, and whatever remains I'm calling this function f, which I don't know. And then I looked for a solution of that function f. And so here we obtain the function f. Then your friend proposes that let's assume that f is time independent, f is position independent. Well, that's an assumption. But if we can find a solution that is position independent, then I have a single solution and I'm done. But this tells me that psi dot f plus f dot psi, this should be equal to 0. And remember, psi is equal to square root of 2 over omega of t sine n pi over omega of t, n pi x over omega of t. So psi dot is equal to del psi by del omega times del omega by del t, which is del psi by del omega times v. Let's take the derivative. Well, the derivative with respect to omega would be square root of 2 over omega t times minus 1 over 2 omega times sine plus the derivative of the sine with respect to t would be, with respect to omega, would be minus n pi over omega squared x times cosine n pi over omega times x. This is psi dot. Times v. Well, it doesn't seem to be presenting too much hope. You see, let's just substitute it. Psi dot, we know that it is square root of 2 over omega minus 1 over 2 omega sine of something minus n pi over omega squared x cosine of the same thing times f plus f dot. Psi is square root of 2 over omega sine of the same thing. This should be equal to 0. Well, you see this, these arguments over here, they're all x-dependent. X-dependencies do not cancel. So we assumed by an x-independent f, but we ended having an x-dependent f. So the solution of this equation will depend on x, so no. So he made an assumption that just didn't seem to work.
Just about this assumption, how would you get that psi dot f plus f dot psi is 0?
Well, let's see. Do you agree with this equation over here?
Which one?
This one.
Yeah, okay.
So this is the equation that we need to solve. We know what psi is. Okay. Now he said that let's assume that f is independent of x.
Okay.
So all its
f dot drops.
not f dot, f prime drops. F prime drops, f double prime drops, the left hand side drops. Yeah.
Yeah, okay. I thought it was like.
So it just doesn't seem to work, that assumption. So what would you like to try? Is this equation correct, by the way? So let's see. The x derivative, the exponent doesn't depend on x. So find that the exponent doesn't influence the x derivatives, the time derivatives. Okay. So that's kind of it. And then we have this differential equation over here. And psi double prime and this psi cancels this e. So we are left with this equation. Let's look at the left-hand side. And for the time being, the book just gives the answer, so I'm just trying to derive it rather than writing down the answer. So let's look at the left-hand side. Let's try if, for example, f is 1. We know that the initial condition was f should be equal to 1. If you put f is equal to 1, for all times and positions, the left-hand side is 0, the right-hand side is non-zero, so that's also not a solution. Let's put the psi and see whether we have some simplifications. Yeah, the same problem. And we said that psi should be equal to square root of 2 over omega t sine n pi over omega x. Now let's do one more thing. Just to simplify the calculations a bit. I will take this as our psi. That time dependence, I just dump it into f. So nothing that I did until this point changes. So this will probably simplify my calculations a bit. So if this is psi, I know psi prime is cosine n pi over omega x times n pi over omega. And now psi double prime I don't need. And psi dot is equal to n pi over omega times minus omega dot over omega times cosine n pi over omega x. Do you agree? Let's put it all up. So we have minus h bar squared over 2m. Yes, there is an n pi x. Or let's say this is equal to minus v over omega times x times psi prime. If necessary, I will put the psi prime back. So this minus h bar squared over 2m twice psi prime f prime plus psi f double dot. This should be equal to I h bar minus v over omega x psi prime f plus f dot psi. Minus h bar squared over 2m psi prime times 2f prime plus I h bar v over omega x f multiply with psi prime plus minus h bar squared over 2m f double prime this is I h bar minus I h bar f dot psi. This is equal to 0. Okay, do you agree up to this point? Well, it would be nice if both of these equations are 0. Both of these parentheses. If we can do that, I don't know. I mean, what I'm trying to do is just do some assumptions, whichever ones you like. We gave it a try, it didn't work. So I'm just put in the definitions of psi. So I obtain this equation. So it will, if this equation would be satisfied if both of the parentheses are 0. I don't know if that will, I can find a solution for that, but we can just give it a try.
We use separation.
I don't know. Let's see. Let's start with the first one, because the first one only involves position derivatives. So it tells me that minus h bar squared over m f prime or plus, this should be equal to I h bar v over omega x times f, or f prime should be equal to I m v over h bar squared omega f times x. So this tells me that f of x should be equal to e to the power I mv over 2 h bar squared omega x squared. So this is not h bar squared, this is just h bar. Times some function of t. If I put this function into the first parenthesis, then it gives me 0. Now let's try to satisfy the second one. The second one, I mean, if I want the first parenthesis to be equal to 0, this should be the general form of f. Well, let's see if it will also make the second one 0. Or if we can choose g such that the second one will be 0. So let's see, minus h bar squared over 2m. Now I need the f double prime. Well, f double prime, let me, I will just use the f prime. F prime is I mv over h bar omega f plus x f prime. This is f double prime. Minus I h bar f dot. Is this equal to 0? Can this be equal to 0? Well, we know what f dot is. Minus h bar squared over 2m I mv over h bar omega f plus x. Well, f prime is IMV over h bar omega x times f Now let's see this plus minus I h bar. Well, f dot is g dot times f over g. I don't want to write the all of f. Minus I h bar g times, well, the derivative of this thing depends on time through omega. So that thing derivative with respect to omega, that would give me IMV divided by 2h bar omega squared x squared times minus v. Well, let me not write this one times f. Well, so I'm writing f dot. F dot, I need to take the derivative of the first term times the second one, that is this first one, plus the derivative of, plus g times the derivative of the remaining. Well, the derivative of the exponent will just give me an exponent multiplied with the derivative of whatever in the upstairs. Well, g times the exponent is already f, so I should choose g such that this should be equal to 0. Now, there are x squared terms. So if this is an equation for g, which depends only on time, there shouldn't be any x's left. X's should cancel. So let's see if they cancel. So here we have I times I, that is, brings a minus. Minus makes a plus. Here I have minus I times I plus minus makes a minus. Okay, that is kind of nice. What else do I have? Here h bars will cancel. There also they cancel. Let's see what else we have. I have omega squares in the numerator. Here also v squared in the omega squared in the denominator, v squared in the numerator. They are common. And I have m squared divided by m is just m in the numerator, m in the numerator. They all cancel. So this term will cancel completely this one. Agree? Now what is left? Well, let's see, m's, this cancel, minus I h bar v over 2 omega f minus I h bar g dot over g times f. This should be equal to 0. Okay, f's also cancel. So I can cancel the h bars, I can cancel the minus i's. So g dot over g plus v over 2 omega, this should be equal to 0. G of t is equal to g0, whatever that is, e to the power minus v over 2 omega times t. So f of x and t, this just turns out to be g of t, g0, e to the power minus v over 2 omega times t, times this exponent. Well, there's one thing I don't like. This is my f of xt. And what else I know? I also required that at t equal to 0, this should be equal to 1. I cannot find such a solution. That boundary condition is not satisfied. Because of, hold on. What I want is that at t equal to 0, this should be equal to square root of 2 over a. to satisfy the proper normalization times some phase. So f of x at t equal to 0 should be equal to square root of 2 over omega at t equal to 0 times a phase at most. So this tells me that G0 is equal to square root of 2 over a. So phi of xt is equal to square root of 2 over a sine n pi over omega x e to power I mv over 2 h bar omega x squared e to power minus v over 2 omega t e to power I over h bar minus I over h bar e of t prime dt prime t going from 0 up to t.
Omegas are also X. No, this is for T.
Omega has time dependence. Well, there is one thing that I don't like. You see, e of t is a real number, so the last factor is a pure phase, time-dependent phase. The first exponent is also a phase. It doesn't change the normalization. E to power minus v over 2 omega of t as time increases. No, hold on. You see, there's something. Okay. Now I know my mistake. You see, the solution of this equation is not this one. The solution of this equation. So that is where I made the mistake. At least one mistake. Why is not the solution? Omega is time dependent. So this is not the solution. So the above differential equation tells me that the time derivative of the logarithm of g plus 1 over 2 times the time derivative of logarithm of omega, this is 0. Time derivative of the logarithm of omega is the derivative of omega, which is v divided by omega. So this tells me that the time derivative of the logarithm of g plus logarithm of square root of omega, this is 0. So g is equal to some g0 divided by square root of omega, g of t. Furthermore, I know that g at t equal to 0 should be equal to square root of 2 over a. That's my normalization. So this tells me that g0 is equal to square root of 2. So g of t is equal to square root of 2 over omega. Remember the factor that we canceled? We included in the definition of f. So it's just this factor. What remains is just 1. So f of t is square root of 2 over omega, f of xt. Times this exponent times this one. So phi of xt, let's say phi n of xt, the solution of the time independent Schrödinger equation that at time t equal to 0 is in the nth state, is equal to square root of 2 over omega sine n pi over omega x e to power I mv over 2 h bar omega x squared minus I over h bar integral of e of t prime dt prime from 0 to t. And En of t prime is equal to so we have the exact solution. So here we have a problem in which the potential depends on time t, but nevertheless we can find exact solutions. So what? Now the next hour we will see what does this mean. So I mean, remember what we are trying to prove eventually, or at least show it explicitly, that if the parameter is changing slowly, so that this is, let's say it is in the nth state at t equal to 0 for my given potential, if the wall is moving very slowly, it will always stay in the nth state at a later time t. Now, any questions on this derivation? Now, what we did was, we already know what the solutions of the the eigenvalue equations for our Hamiltonian. So if the parameters were time independent, then it will, as its time evolution, it would just receive this factor, this exponential factor. So we said that, okay, so let's add another factor, which will take into account the modifications of my wave functions due to the time evolution. And then we just solve for this unknown, the unknown function f is f. So we solve for the f. We found one solution using making certain assumptions. We made assumptions. But nevertheless, we know that the solution has to be unique. Solution of this equation subject to initial conditions has to be unique. So since we could find one of them by making assumptions, we know that it is the only possible one. So even without the assumptions. And that solution turned out to be this one. So we have a system which we can study exactly, and that is what we will do. So we will see how the adiabatic approximation works in this exactly solvable example. And then afterwards we will try to generalize this.
So how slow?
We will see. I mean, that is a good question which we have to address. Because we cannot say that the change of something is slow, because the change of something is measured by let's say, the derivative. Whatever parameter you have in this example, it is the width of the potential well. It is derivative has the units of velocity. So velocity, we cannot say that velocity is small or large. So what does it mean to be slow? So we will also see it here. So that's one place where we can, in fact, start. What are the parameters in our problem? What are their dimensions? Do we have something else which has the dimensions of velocity so that we can compare the two? We can say that, okay, we have this parameter which has the dimensions of velocity, plus we have the velocity of the speed of the wall, and then comparing those two, we can say that, okay, the speed is slow if it is smaller than this one or not. Okay, let's give a break, and then we will continue.
By the way, do we have the velocity speed?